Now we have all the information to write the link budget for the uplink and the downlink of the Voyager mission. We have seen the data for the space segment, for the probe. Now some images and data for the ground station, for the Earth station. At the time of the Jupiter encounter, it was a 64-meter antenna, and you can see the reflector. There are 3 of them in Madrid, Canberra, and Goldstone, California, and they have a main reflector, a sub-reflector, and the feeds here. And all the electronics, all the cryogenic part was down there. And they could really cover different frequency bands, and the antenna could be oriented in any direction of space. And this is the basic Deep Space Network, or DSN, antenna that is still alive and working well. The typical parameters at the time, 1979, at the time of Jupiter, was 64 meters, and there's no problem in transmission. They could send powers up to the order of hundreds of kilowatts, so they had plenty of power to send down from the Earth. There was no problem of selecting a power level. The gain of the antenna was limited to 60 dBs, and it was right-hand circular polarized at S-band. At the downlink frequency, which is more or less the same, it's a little bit different, but it's the same, the antenna is just 1 dB larger, and now the system noise temperature is around 22 kelvins. This is just the number. And at X-band, the gain of the antenna is 10 dBs larger, because we have increased the frequency, and the system noise temperature is 28.5, and could receive or transmit in right or left-hand circular polarization. And now, let's go for the link budget. We have here a typical link budget in a compact way. This is, you will find it in a spreadsheet format in general. And here we have the parameters, and we'll start with basic parameters from the transmitting antenna and then to the receiving antenna. And we have 3 different columns in this case. The first 2 are for downlink, for the data that is being sent from the Voyager to Earth. And here you have at 8 GHz, at 2 GHz, X-band and S-band. Okay? And on the third column here, we have the uplink, that's from the ground station to the Voyager. And this is at S-band. There's a color code in this image. We use blue for the data that is related to the spacecraft, to the probe, and black for the data that is related to the ground station on Earth. Okay, so this is just the code for the colors. So let's start briefly. On the first line, we have the carrier frequency, 8.4, 2.3, 2.1. The wavelength is simple to find, it's just the speed of light divided by frequency. This is just the number. In one case it's 3 centimeters, in the other is 13, 14 centimeters. So we are talking about short wavelengths, but not really too small. And this is related to the size of the antenna. The diameter of the antenna on the spacecraft is 3.7 meters, on Earth 64. The gain, 48 or 35 on board, 60 dBs on Earth. Now, the first interesting parameter here is the equivalent isotropically radiated power, which is the product of the transmitter power times the antenna gain. And in this case, you have here the power, you have here the gain. In this, we have transformed the power in watts to dB watts. It's 13, it's 10 log of this number, gives you 13 dB watts. And the same in the others. So you just add 13 and 48 and you get 61 dB watts, which is equivalent to 1.3 megawatts. Although we are putting 20 watts of power, this is equivalent since it's highly focused, to 1 megawatt spread over all directions. And that's the meaning of this parameter. At S-band is lower, 43, and on Earth, assuming 10 kilowatts, gives you the equivalent of 10 gigawatts, 100 dB watts. This is a very powerful stage. So this is not the problem. This is not a limiting factor in this communication system. The problem is with the probe, certainly. The distance to Jupiter is 680 million kilometers, and this gives you a free space path loss, which remember is lambda divided by 4 pi, the distance, of 287.5 dBs, 276 to 75. Just to make a comment on the meaning of this. Once again, if you put 1 unit, that's your reference, what you will get, this number means that you will get 0.28 zeros and then a digit. That's what we are talking about. Okay? So this is just the free space path loss. And with all those parameters, we could immediately compute the power flash density that is arriving to the antenna. In this case, to the Earth station, to the ground antenna. And the order is, if you just put the equivalent isotropic radiated power, you divide it by 4 pi the square of the distance, gives you 2.210 to the minus 19 watts per square meter. The order of magnitude of this is 0.2 atto watts per square meter. And I don't want to give you already the number for this. You see it's 100 times lower. And here is not that bad because we have a high power. So this is the power that is being received on Earth. This is the power density that is being received on the probe. Now we continue. That was the transmission part, and now let's go to the receiving part. On the receiving part, here, now we are going from the Voyager to Earth. The antenna on Earth is 64 meters, 61 dB and 71 at those two frequencies. Look at the effective area. This is about 1,300 square meters of the size. It's a very large size antenna. Okay? While on the Voyager is just 4 square meters. The received power is just the product of the previous power density times the effective area of the antenna, and this gives you this number. Okay? And this number at X band is about 0.3 pentowatts, which is a small number too. Here we are at the level of the attowatts, and now the system noise temperature will let us, with the figure of merit of the system, find the signal to noise ratio. The receivers on Earth have the minimum possible noise temperature that one could really imagine or work. This is where all the effort went, to diminish as much as possible the noise temperature of the system. You can either work the G over T or go directly to the noise power spectral density. This is just Boltzmann constants times the system temperature. Okay? Now with this, what we now do is find the total noise power. Okay? But in this case, we are finding the spectral density. We are not taking into account the bandwidth or the data rate. We are just finding the noise power spectral density. Okay? And we are going to find not the usual signal to noise ratio, but the power, this is power received, to noise power spectral density. And the units for this are the inverse of Hertz. Okay? Why? Because then we can enter into the picture the data rate and find the hit error probability as is done in the normal way. So now with the signal to noise power spectral density, Here we get 7 10 to the 5th on X band. Here 1.8 10 to the 4. And in this case also it's a larger number. Now we need to find now the energy per bit. And the energy per bit, remember, is just the power received times the time duration of 1 bit, or the power received divided by the data rate. And here you will see that there are different data rates considered. The first one is 115.2 kilobits per second. That's the data rate that was required to send the images down to Earth. Now, when you enter this number, then now you could find the bit signal to noise ratio, which is 8 dB. If you go to S-band and you do the same, but now for the typical maximum data rates, and is below this number now, then you get 7 dBs. And for the uplink, there are plenty of dBs, so you have a very large margin there. But the code we were using required a minimum of 2.5 dBs of the signal to noise ratio for this bit error probability. And this is normally described as the zero margin. We are not considering any other effect. Could be atmospheric losses, antenna pointing, there are different values there. So this number at this bit rate, or bit error probability, gives you that you need at least 2.5. The difference between those two is the margin you have. So things could deteriorate on reception up to 5.5 dBs. If you go beyond this point, then you lose the link. And for S-band, this is for the images, this is for data on other instruments or on the spacecraft, then the margin is lower, it's 3 dBs. Why? Because they require a higher probability of error. Okay? Here you only accept one error in 100,000. Why can't you accept a larger number here? Because this is an image. And there, if you lose some bits, you can still tolerate in the image. You can process the image, you can improve the image. But on the data side, there you don't want to lose any instruction or any relevant bit. And those are the margins that we had for the mission in Jupiter.